Good afternoon, everybody. So let's start. It's 5:35. Can you hear me? Is everything okay?
Yes po, ma'am.
Yes,
Uh-uh.
ma'am.
Yes po.
Yes po.
Okay, nakapost na sa Oble ang ating lecture activity today. So I'm gonna share my screen and look for it. So Oble. Oops. Kumusta kayo, guys? How are you doing? Kumusta ang mga ganap? Uy, react!
Buhay pa naman, ma'am.
Ibali, malapit na ang reading break. Alright, sige. So, sa 301, then, banda dito, kunin natin ang activity. Oh, by the way, before we do this, just housekeeping. Open ka. Yan. Okay, tandaan, nandito na po tayo. Okay, we're still under multi and hyperspectral imaging, and the number of hours I've devoted for this topic is 5, so that's why. So there will be actually 2 activities for this topic, but just 1 report. Okay, that's why 2 weeks yung deadline kuno. So there will be another activity na related to principal components analysis. Okay, right. And then let's move to the lecture today, which is this. Teka, mag-stop share muna ako kasi hindi nag-show up yung nag-pop up. Share screen again. There. Share. Yan. Tapos, ano nga ba uli? F11 ba, guys? Ano nga ba uli yung pang-large screen ito? F11 ba? F11. Control. Ano nga ba? View. Ano nga ba yun, guys? Dito sa, Paxit Reader, ano ba yung view nito na mas malaki? Pumunta ko na. Control J ba? Nope. Hindi man F11. Nope. Okay. What happened? Ay! Ayan. Wait lang ha. Wait a minute. Just a moment. View. Okay. So, principal components analysis. Let's go through this lecture. So, our 2 objectives is to first derive eigenvectors and their eigenvalues from image and spectral data. And the second is convert a digital camera into a spectral imager using principal components analysis. Okay, so let's go through the derivation of the principal components analysis. So PCA allows the compression of a high-dimensional feature vector to a fewer number of coefficients. So a shorter vector, in other words. In this activity, we employ PCA to find the few basis functions that can represent our data ensemble through a linear superposition. Now, the derivation that we're shown here, that we will show here, is based on the Karhunen-Loewe, so wrong spelling, O-E-V-E, dapat yan, expansion, KL. So the KL expansion is an orthonormal expansion of a vector X using the eigenvectors of the covariance matrix of the data set where X belongs. So this representation of a data set by select eigenvectors is known in statistical literature as principal components analysis. The eigenvectors possessing the highest eigenvalues are used for the reconstruction of data, while those with 0 and low eigenvalues can be discarded thus reducing the dimensionality of the feature vector space. Okay. So let X be an n-dimensional random vector, which can be represented by an expansion of the form X is a linear superposition of coefficients yi times some vector phi sub I equals 1 to small n. Or we can write it in this way. No? The components, matrix operation, matrix vector multiplication. The components of phi span the n-dimensional space containing X and are called basis vectors. So phi is a matrix and its components, columns for example, are the basis vectors. Dapat ata may transpose ito. Okay. If the components of phi form an orthonormal set, then ibig sabihin, well, if I and j are not equal, then it's 0. Otherwise, their dot product is 1. Okay. Then the components of y are given by yi is equal to just phi sub I transpose times x. Yan. So these are the coefficients yi. Lino pa naman. So y then is an orthonormal transformation of the random vector and is also a random vector. Each component of y is a feature which contributes to representing the observed vector x. We now want to use only m, which is less than n, components of y to at least estimate x. So replacing the uncalculated components of y by constants b, we will form the following estimate. So an approximate x with just m components will be a summation from 1 to m of yi, phi, and then there's an additional term here. Yun naman yung indices na starting from m plus 1 to n, sum of b sub I, phi sub I. Okay? Now, this estimate, if we were, so essentially, parang ito lang gagamitin natin, ano? But meron pang parts dito, right? So this estimate introduces an error given by x minus this x tilde of m. Okay? And that is just substitute equation 4 over here. And then, if we substitute equation 1 for x, meaning yung x being summation of yi times phi sub I, right? Then, we get this. So, essentially, sinubstitute lang natin ito dun sa x. Okay? And there we have it. So, mawawala yung first m terms, di ba? Kasi yung summation ng x is from 1 to n. Eh, since meron kang term na ganito, matitira na lang is I equals m plus 1 to n. Okay? So, we get delta x tilde is equal to equation 6. Our objective now is to determine these b's such that we minimize the mean square error. So, let's define the mean square error this way. This is equal to the expectation of the norm of delta x squared. Okay? Or if we write this out, okay, it would be, since square to, no? This will be the expectation of the summation of I equals m plus 1 to n, summation of j equals m plus 1, n, y minus bj, y, I minus bi, phi, teka, tama ba? Tama. Yj minus bj and yi minus bi, and phi sub I transpose times phi sub j. Okay? expectation. So now, if you carry this out, siyempre, pag expectation ng constant, 0. So, ang matitira na lang at saka isa pa, since ito, magsi-0 kapag I is not equal to j, so matitira na lang ito. Yes? So, let's assume na natira na the I components na pareho yung I equals j. So, wala na yung dalawang summation, ito na lang natira. Next, so gusto nating i-minimize tong mean squared error. And so we do the derivative test where we take the partial derivative of the mean square error with respect to b and then set that to 0. So that means partial the derivative of e, the expectation of this equation here with respect to bi. And we're doing it for each I. So remember, this is a summation form. So for each I, may kanya siyang ganito. Right? And so if we perform this partial differentiation, we are reduced to this. Okay? Alright. And this must be equal to 0. So this implies that if this equation equals to 0, then b sub I should be equal to the expectation of y sub I. Okay? Or the phi, so yi, express that in terms of x and phi, then you get this, no? And phi, this is a basis vector, so this is a constant, so you don't have an expectation for that, so you factor that out, so you're taking the expectation of the random variable x there. So bi is given by this. So now the mean square error, that's for a subscript I, no? So there are different i's, can be written as, okay, all right, the error is we substitute the value of b that we found from minimization, ito daw siya, and so we substitute that in here, in this equation. So calculate natin yung b, papasok natin dito. B is equal to this, pasok natin doon. Okay? And so, ito na yung mean square error. Okay? And now we put back the sum. Alright? So that will take care of the subscripts of I. And now, this summation says it's the mean square error is equal to the sum from I equals n plus 1 to n of the expectation of this quantity yi minus expectation of yi quantity squared. Now let's substitute yi in terms of the phi and the x, and so we get this term. So summation, the expectation of this term quantity squared. Now kung imagine mo yan, kung squared to, no? So parang may square to, you can factor this out kasi it appears both in this matrix operation. So the square nitong nitong part na to can be expressed this way. So you have phi here transpose and the other phi here. So together they take care of the square in here. Tapos you're left with quantity x minus expectation of x squared. So quantity x minus expectation of x squared. So in matrix operation, it's the same as you take x minus expectation of x, so, and then multiply that by the transpose of the same x minus expectation of x. So that's how you take the square of this vector here. Okay, and therefore, if you think about this, the expectation of this a variable minus the mean, okay, a random variable minus the mean of the sum of x, okay, and multiply that by that difference again, transpose, call that r. This r here, expectation of that is nothing but the covariance matrix. Okay, so you have the phi outside, transpose, so phi I, and then multiplied by r, which is clearly the covariance matrix of x, and then multiply it by the transpose of phi, okay, and sum over I from m plus 1 to n. And again, R is the covariance matrix of X. Now, doesn't this look familiar? This looks like eigenvalue equation. Okay, so the thing is, we want to know phi, because that phi will give us minimized error. No? So the optimum choice, when you have an eigenvalue equation, the optimum choice for the basis vectors are those which satisfy this equation. That covariance matrix R, no? Okay, multiplied by, say, this eigenvector, we call this phi eigenvector, is equal to some constant, lambda sub I, times this same eigenvector. And for all i's yan, for different eigenvectors. Okay, so R is the covariance matrix times this eigenvector sub I is equal to a constant, which we call the eigenvalue, times the eigenvector. Okay, so if we substitute that here, okay, so we'll have an identity matrix, and malalabas lang tong constant na to. Thus, the minimum mean square error is equal to just the sum of the eigenvalues from I equals m plus 1 to n. There. Thus, the effectiveness of each feature is determined by its eigenvalue. Okay? The higher the eigenvalue, the greater the contribution of the eigenvector, or the principal component, as it is also called, to the variance of the set. So to minimize the dimensionality, the smallest eigenvalues should be deleted first. This means that if the eigenvalues are indexed in descending order of so when we order or we arrange the eigenvalues in descending order, the largest is the first, so, and their corresponding eigenvector is also uh, sorted according to the value of their eigenvalue, then we say that the first m eigenvectors are the ones that contribute the most to the representation of the data. Okay, so that means, because this is our error, the m to the m plus 1 to the nth eigenvector can be discarded because their eigenvalues are assumed to be small. Okay, so just to explain further, I'll stop sharing here. Share naman ako dito sa kabila. Click. Again, share screen. No, so hindi. Share whiteboard. Oh, yarn. Okay. So, di ba pag may teka ba tayo sa malayo? Pag meron tayong ganitong nakikita. Okay. That reminds you of the eigenvalue equation, ano? So, para ma-solve ito, gusto nating makuha ito. So, this is the eigenvalue equation, and what satisfies that would be this, right? Okay, where this lambda is this is a coefficient, so it's a constant, no? So this is a matrix, this is a vector, this is a constant, this is a vector. Okay, and to compute this, technically, to compute these eigenvectors, what do? You actually try to diagonalize the covariance matrix. So, habang dinadiagonalize, so, kunyari, yan yung covariance matrix mo, no? Ito yung R mo. Okay? So, may mga values yan. Values yan. Non-zero values, perhaps. Natin. So, para natin ma-solve ito, gusto natin siyang i-diagonalize. So we want to convert this vector, this matrix into a diagonal vector. And actually, yung after ma-convert mo siya, okay, into a diagonal matrix, okay, essentially, ang ginawa mo, wait, whoop, whoop, whoop. Essentially, naghanap ka ng phi na makakapag-produce nito. So, while you are diagonalizing this, ewan ko kung natatandaan nyo yun sa matrix, ano nyo, no? There are many ways. If mamanu-manuhin natin to, there are several ways of diagonalizing a given matrix, right? And as you perform that operation, na-modify mo yung phi. By the time that you diagonalize it, you finally come upon the proper phi that will reproduce this diagonal matrix. Okay? That's why ibig sabihin nito. Ano naman ibig sabihin ng pag-diagonalize ng matrix physically, or rather, kung imagine niyo sa feature space. Now, how do I make a new page? New whiteboard. Okay. Essentially, suppose we have data in feature space. This is feature 1 and then feature 2. So, yung data natin, each of our data point has a feature 1 and a feature 2. Okay? So, kunyari, ito yung unsum of data natin. Okay. Finding the principal components essentially is, una muna, di ba, kukunin natin yung covariance matrix. Ano ba yung kailangan sa covariance matrix? Di ba pag nagko-covariance matrix tayo, hanapin mo yung x, subtract mo yung mean. So, essentially, may idea ka dapat kung ano yung mean. Doing this operation is known as mean centering. Siyempre, yung covariance then would be yung kukunin mo yung x minus e of x transpose, right? Mean centering means, pag kinuha mo na tong part na to, ibig sabihin, itong origin na to, ng feature space mo, move mo dito, sa gitna niya, sa mean nito. Itong data mo, no? And then, what do you do next? Hahanap ka ng transformation. In a way, kung iisipin nyo, the diagonalization of a matrix is a rotation of the space, no? So, diginita na natin yung, nandito na siya, let's use a different color. Okay? So, kunyari, na-move na natin dito. This is the mean-centered F1. So, mean-centered na yan. Mean-centered F1. And F2, mean-centered. Mean-centered. Okay? What next? In principal components analysis, after mean centering, you actually, diagonalization of a matrix is actually akin to rotating the axis, the feature space. So, ito, saan ba highest ang variance? So, when you transform by rotation the feature space, titignan mo by what rotation will it produce the highest variance. And notice that if we rotate the axis this way, diba? And this way, so let's call this our new basis vectors. Okay. If we think about this unit vector pointing in this direction and this unit vector pointing in this direction, essentially, these are our new eigenvectors. Okay? And ito, usually, the first one would point in the direction where the data has the highest variance. So, kunyari, ito na nga yung cloud natin ng data, and it looks like a cigar. So, when you do principal components analysis, you actually rotate the feature space such that the first eigenvector points in the direction of the highest variance of the data. Okay? So, since parang ganyan yung data cloud natin, parang ganito yung ating first eigenvector, and of course the second eigenvector, this is orthonormal, so the second eigenvector should be orthonormal to this. Okay? Yan. Now, ang kainaman yan is sometimes if the data is very very similar to each other, posibleng kunyari the data may look something like this, di ba? It's along a line. Well, this is highly idealized, but think of a higher dimensional data, and if they are very very similar or they have a very large similarity to one another, it may be that in a certain axis they just lie along a line. Okay, and therefore in this case, kapag PCA natin to, ang lalabas dun sa principal eigenvector natin is, or first eigenvector natin is talagang ganon. Notice that kung isipin mo yung variance nitong data cloud, like for example here, the data cloud, ano yung variance yan? Di ba ang variance square root? Square root nun is standard deviation. So standard deviation yung mga ganyan, right? So the eigenvalue essentially is equal to the variance actually. So, yun yung standard deviation, square ng standard deviation along that eigenvector. Okay? So, in this case, in the case na diagonal lahat, ay yung points lie along the diagonal, notice that the eigenvalue along the direction, the second eigenvector essentially, is 0. Wala na. So, this means you can discard this. In representing the data, you don't need two numbers to represent the data. All you need is just one, so long as that value is expressed along this new eigenvector. Iyon yung sinasabi na power ng compression ng principal components analysis. If your data has a very high degree of similarity, when you compute the principal components or the eigenvectors, take a look at their variances or the eigenvalues. When you line them up, okay, you might see that somewhere along the line, some eigenvalues will already have very small numbers or even maybe 0. Pag 0 yung variance niya, ibig sabihin it doesn't contribute to the data, to representing the data. And you might as well just discard the eigenvectors. And therefore, you compress the expression of the data. Instead of having, say, 4 numbers, if the eigenvalue of the fourth, the value of the fourth eigenvalue is 0, you can just discard that, and it will be lossless. However, if the eigenvalues are non-zero bandang dulo, but they are very very small, still you can discard that, but the error that you will get in representing them would be just the sum of the small eigenvalues that you discarded. Okay, so I'll stop share here. Wala yung Apple Pencil ko guys kaya ako makagamit ng ng larger na screen. Paano bang stop share? Stop share. Yeah, there. Now let's go back to the activity that I'd like you to do. The first activity, share screen again, is this. So just to get your feet wet on principal components analysis, let's have a fun activity, group work. Kindly please share 5 images of yourself. So capture 5 images of your classmates' face. Okay, there's 17 of you. So 17 people times 5 captures equals 85 faces. Okay, what are we going to do? We are going to compute eigenfaces. Okay, eigenfaces. We only need low resolution and black and white images, so we just need to line up and take 5 class photos. Okay, maybe you could remove glasses for now, please. Okay. So mag-share tayo ng mga 5 class faces natin in grayscale. And then we just need to prepare them in such a way na medyo aligned. Why faces, guys? Because faces are highly similar, di ba? We all have 2 eyes, 1 nose, 1 mouth, and their locations are the same always, no? So if we line them up properly, like crop the faces to exclude hair, you just include just the feature of the face. Resize the face images to be 50 by 50 pixel only, and then if you could align the eyes, nose, and mouth, then you would have 85 faces to form our face database. Okay, now either arrange the face data into a mosaic or concatenate the image data into an 85 by 2500 matrix. Sorry ha, for some reason sa pages hindi nag-i-expand yung May latex kasi sa pages, kaso ayaw niyang mag-expand to a larger square bracket. Kahit gamitan ko ng slash, / square bracket, ayaw niya mag-resize. Okay. So essentially, yung uh, uh, superscript 1 stands for the person. For first person, second person, up to the 85th person. Yung subscript 1 to 2 to 2500 are the pixels. So again, when you concatenate, a square 50 by 50 pixel will become say a row vector, right? So yun, pag hile-hilera lang natin yung pixel. So para siyang isang line na lang. Okay. And then we line them up like this. So we have an sum of image face, concatenated grayscale faces in row vectors. Okay. Okay. Now, we can do it. What we can do is, now that we have this data, we get the covariance matrix of X, remember? And then we apply the PCA on the covariance matrix of X. So essentially, we want a mean-centered covariance matrix. So you may either solve the eigenvalue equation on cov X or use the standard PCA packages in your scientific software. So PCA already comes in most scientific software. In MATLAB, you could use PCA cov and let it act on the covariance of X. No? Alternatively, meron pang isang pang function available. Instead of getting the covariance matrix of X, you can go straight away and use PCA of X, apply X in MATLAB. So no need to compute the covariance matrix, but do select the centered parameter. So if you look at the help dun sa syntax ng function ng PCA, there is a parameter that you can set. Centered is set to true. So, ibig sabihin, siya na yun magmi-mean center ng data. However, in the output, you have to know the mean, so you can have the mean included in the output. So, PCA does the covariance matrix for you if you set the centered variable to true, and then you include the mean in the output. You would need the mean in the output to compute kung ano yung kinalalabasan niya. And then find how many principal components out of 25,000 possible ones, because in general, the number of eigenvectors that you can get is equivalent to, of course, the size of your original vector, which in this case, if each pixel is a component of a vector, then we have 2,500 components. So, technically, kung gaano kahaba kung gaano ilan yung components mo, yun din yung dami ng posibleng eigenvectors na makuha mo, guys. Pero hindi lahat ng 2,500 na yon is useful. Ika nga, because again, remember, the faces are so highly similar, for sure, hindi kailangan nagkakaroon ka ng eigenvalues na 0 or very near 0. Okay? So, check out the variances. If you normalize the variance, so you take the sum and then you take the sum of all the variances and you divide everything by that sum, you actually get a percentage contribution of each of the eigenvector. And then you take a cumulative sum of these normalized eigenvalues and then find out where it reaches 99% out of these 2,500 possible ones. Then you see that, okay, we can stop here and then cancel all the rest after 99%. So that's where the reduction comes in. Okay? And then, I'll ask you to reconstruct the faces using the linear superposition of weighted eigenfaces. So essentially, from our database of our own faces, we will compute the eigenface. And then, we will represent each of our faces by a linear superposition of these eigenfaces. Okay? So that in that way, you see, ganito pala yung principal components. So, you can represent the face by a fewer number of parameters. Okay? And then comment on the quality. So this is the first activity. The second activity will actually be the one where we will use the concept of PCA to convert our ordinary cameras, like our smartphone cameras, into a digital spectral imager. Okay? So first, something fun muna. Okay. Any questions about this? Yeah, I'll stop share. Stop share. Okay. Medyo, malinaw ba yung derivation, guys? And may tanong ba kayo tungkol sa activity? Hello?
Dapat po, ma'am, front-facing yung photo kung ganun.
Sa ngayon, yes.
Okay.
Para kayong mugshot.
Okay pa.
Okay, mugshots. Okay. So, ganito, no? In simple terms, ang any face, para siyang Fourier series, ano? 'Di ba sabi sa Fourier series, any signal can be represented as a linear superposition of sinusoids with appropriate coefficients, frequencies, and amplitudes, right? So you can decompose any signal into a linear superposition of sine waves. Basta alam mo yung appropriate amplitude for that frequency of sine wave, alright? And then you sum them up, right? Imagine niyo, ito naman ay sa images. Okay? Any image or any signal, kahit spectral signal, can be represented by a linear superposition of eigensignals. Unlike Fourier series, guys, i-compute mo kung ano yung eigensignals na yon. It's statistically derived. It is statistically derived. In fact, galing siya sa covariance matrix. No? Okay? By diagonalizing the covariance matrix of your sum of data, you will be able to compute the eigenvalues that will best represent your data in the most compact manner. Okay? Gets niyo ba yan? So, imagine niyo na yung high dimensional signal natin is a phase image. Phase image. 50 by 50 na pixel phase image is already 2,500 data points. So, para kang may signal na 2,500 components. Imbis na ang i-feed mo ay 2,500 numbers to represent a phase, what if I tell you that actually you probably need just 25 numbers to represent a phase? Wow, 25 versus 2,500. Diba? Laking reduction yun. Okay? So that's where the compression lies. If this is also used also in deep learning. For example, you have large data sets, and then masyadong mahaba yung dimension ng dataset mo. Baka mamaya kung may unsum ka ng dataset, baka hindi naman how it is represented now need not be the way it should be presented to, say, the network or to a machine learning algorithm. Kasi baka pwede pa siyang i-compress. No? So PCA is a form of compression, but it also is a form of finding out what are the components that make up the data. And sometimes finding these components give insight about how the data is formed or how the data behaves. No? Okay. Anybody here who has experience now using PCA? Raise hands naman dyan, guys. Isa. Sige, Senech pa. Chester, Christian. Very good. Okay. Matthew, yes. Nagamit nyo na ba siya on images like faces? Perhaps signals?
Di pa, ma'am. Parang sa spectrum lang.
Chester, saan nagamit? Yes. Sa image ka rin, Christian. Yes.
Image, like for data sets po. You're assuming kasi na uncorrelated yung dimensions. So for example, dito po sa 50 by 50 thing natin, yung 2,500 long na feature vector mo, you're assuming that each dimension is unrelated.
We have no assumption at all. Kaya nga,
Yes.
pag nakakita tayo ng correlation, that means, insignificant na yung isa kasi if one changes, the other changes as well. So makikita natin na katulad ng illustration ko kanina na lahat ng points ay lie along a diagonal line, they're highly correlated. So might as well just use a single number to represent that data on the diagonal, right? So we have no assumptions at all. Wala tayong pake kung correlated ba or uncorrelated yung data. Instead, PCA, if you have a bunch of data, you have no idea kung may correlation siya, it can actually tell you if there are correlations. If there are correlations, you will have eigenvalues that are 0. Yun. Christian, anong image ang ginamitan mo? Ang image ba ang gamit mo, Christian, dun sa PCA mo?
Sa face maps po.
Face
Ah,
maps?
face maps.
P-H-A-S-E or F-A-C-E?
Apo. PHASE po.
Phase maps. O siya, convert natin yan sa phase maps. Ito naman, F-A-C-E. Now, yung principal components kasi,
Para na-try ko rin siya, ma'am, sa normal.
sa faces din? Sa?
Like normal image, na-try ko rin siya. For example, flag. Pag nag-PCA ka, pwede mong makuha yung certain parts lang ng flag. Parang ganun ba?
Yeah, right.
Yung ganun yung nagawa.
Okay. Alright. Do you know that, di ba sabi ko, actually, medyo kahawig na kahawig sila ng Fourier series. In fact, in the limit of infinite images, the eigenvalues become the discrete cosine transform. Okay? In the limit na maraming images, makikita mo yung mga for example, I'll give you an example. JPEG, guys. Di ba yung mga images natin are saved in JPEG? Paano ba ginagawa yung JPEG? Actually, pag kinompress mo yung image mo in JPEG, you chop your big image into 8x8 squares. So, may malaki kang image na, tapos isa sub-image mo siya 8x8. Yung kada 8x8 na yun, ipapass mo siya sa discrete cosine transform. So, since 8x8 yung image mo, ibig sabihin may 8x8 8 frequencies along the X, 8 frequencies along the Y. So, you can have as much as 64 DCT coefficients corresponding to frequencies along the X, frequencies along the Y, and their combination. Okay. Do you know that you can do the same using PCA? So you can compress an image by chopping them into small squares, again, pwedeng 8x8, and then computing the PCA for all those chopped 8x8 images. Okay? And then you'll end up with eigenpictures. These eigenpictures are 8x8 images, but they're not just images na zeros to 255. No, they actually have negative values as well. So, parang real numbers ito, no? And a linear superposition with some proper weights of these eigenimages can reconstruct that 8x8 image where you got it from. Okay? So, kukunin mo lang yung dot product ng image mo na 8x8 original dun sa dot product niya with those 8x8 eigen images that you got, and those are already the coefficients that you save. Okay? And the compression in JPEG goes that way. You save just the coefficients. You only save the coefficients. And it may be, depending on the compression level that you choose, you could have lesser and lesser coefficients that you need to save. And yet, the image would look fine, acceptable. Okay? Alright. So, this is, hopefully this is fun because it's your faces. Possibly, unfortunately, ito yung hindi pa to 3D. In the nature of nangyayari tong nauso tong eigen faces dahil back in the 1980s nagkaroon ng competition na DARPA ang nag-sponsor nitong competition na to ay yung army ng US, no? So they have these competitions. There's a nice reward. Sino makakapagawa ng best face recognition algorithm. At ang nanalo is one based on eigenfaces. So, dahil complex nga ang masyado nga malaki yung dimension ng face. So, by using eigenfaces, na-reduce nila yung a face can be represented by just a fewer set of numbers, and they use that number, those small set of numbers for the classification. Okay. Do you know also that it is enough na ang size ng face ay 10 by 10 pixels at medyo maaanidad mo na kung sino yan? Yes, there's a study na kahit 10 by 10 pixels, ang lito na, no? Imagine niyo ngayon, mga screens natin, 1920 by 1080, tas 10 by 10 lang, tas may mukha doon sa 10 by 10 na yun. And yet, recognizable pa rin yung face na yon kahit 10 by 10 pixels lang or 100 points lang. Okay. But ngayon, ang interesting ngayon is medyo 3D na. So, the reason why we have all those nice filters sa ating phone na yung mga bulaklak sa ulo, mga beard, mga glasses, ganyan, na gumagalaw as we move our head is because ang technology na ngayon is imbis na eigenfaces, 3D models of faces. So, again, very similar yung pagiging 3D ng ating face. Of course, we have a forehead, our eyes are recessed, our nose is forward, etc. We have cheekbones, we have chins, ganyan. And this is very highly similar. So, imagine, no, imbis na eigenfaces ang meron kang parang eigenmesh. And then you just fit it to the face. So kahit gumalaw-galaw yung mukha mo, 3D na yung mesh, no? It's a set of vertices representing your 3D face, shape of a face. Kahit gumalaw-galaw, okay? Nakukuha pa rin na, okay, this is your face, okay? And this is this is the location of your eyes, nose, chin, mouth, okay, head, ganyan. Alright? So that was a breakthrough. Okay? Ang gumawa nung technology na yon are two Eastern European graduate students, and they sold that technology. Quite explosive use of that technology actually. Dati kasi kailangan pang maglagay ng fiducial points sa mukha. Imagine niyo guys, yung mga CGI dati, they had to have a camera pointed at the actors, and this small camera is attached by a frame to the actor's head. So habang nag-i-emote yung actor, have you ever seen this when the actors are performing and CGI or computer graphics will be embedded on their face, or rather will replace their face? Perhaps sa Avatar, perhaps nakita niyo yun. Even si Smog, okay, the actors has dots on their face, have dots on their face. And actually, the camera is just following these fiducial points para may 3D image, may 3D cast yung face ng para masundan yung expression ng actor, and then i-overlay nila yung CGI. Okay. But now, imaginein mo, because we have very similar face structures, it's now an eigenmesh anyway. Okay? Alright, so after this activity, we will move to hyperspectral imaging. So, we will again use PCA, this time on reflectance spectra. Any questions? So again, welcome. If you have a need for a tutorial, just tell me, then we can discuss on Friday. No more questions? Kung wala na, going once. Ma'am, ipopost rin po ba yung tutorial? Yes. Sorry. So may mga, ma'am, popost nyo rin ba yung tutorial for the... Oo, pasensya na, nakalimutan ko. May video na tayo nun. Uploaded na po ba yung lecture last week? Yung video, hindi pa. Sorry, Lemuel, and sorry, Christian. Yes. You're talking about, guys, yung video? Yung code, parang ka na, no? Na-share ko na. Yung video na lang nung lecture, ang hindi pa, right? Thank you for reminding me. I forgot about that. Okay. I'll do it. Sige. Yeah, Jonel.
Ma'am, question po. Yung deadline po ng lahat ng activities sa end of SEM pa, no?
Oo, kaya naman yung nag-ask ng
okay
ng
po.
deadline. So, linalagay ko lang dyan pang pa-stress.
Okay po. Alam po. Kasi yung sa activity 1 po kasi nakalagay na deadline is sa May. Pero yung sa activity 2, overdue na po.
Nasa-stress ba kayo dyan, guys? Pwede ko naman tanggalin yan eh. Parang, I think, yung some of
Okay
you
lang.
requested that para lang may para lang may pacing. Pero kung
Okay lang
na-affect
po
ang inyong
sa
mental
akin.
health, okay lang ba? Naiwan
Okay
yung,
lang po, ma'am, para may sense of urgency.
Okay, sige.
True.
Pero chill lang kayo ha. I mean, I want you to enjoy your I mean, ano yung guys, nung ako yung PhD katulad nyo, and some of you are already PhD, no? Pinaka-enjoy kong graduate, hindi, pinaka-enjoy kong academic life was in PhD, you know why? Kasi I can choose my electives. Nung MS, stress na stress ako, kaya sorry na lang yung mga nag-MS dyan kasi yan, core courses eh, diba? Pagdating ng PhD, wala ka ng core courses. Yun mga gusto mo lang, mga subjects ang kunin mo. So I took courses in math, yung mga first parallel programming courses, kinuha ko in math and engineering, first time nag-offer sila ng machine learning. Okay? Meron lang nga sanang marine science eh, kumuha na rin ako ng marine science na ano eh, graduate courses dun eh. Pero yeah. So I hope you enjoy. Ang gusto ko lang sana ay mag-enjoy kayo sa mga activities. Hindi kayo ma-stress. Because you'll learn more if you enjoy what you're doing. Okay? Okay na? Tanong tanong? Yeah, Chester, are you saying
Questions
something?
ng report, like we just submit yung slides.
Ha?
Pero contain na siya in the slides.
Oh, yeah. For example, one of your classmates asked, pwede bang written report na lang? Sure, okay. If you're more comfortable with written report, I'll take that too. Basta pareho pa rin yung rubric na
Okay
na
po. As long as yung structure and it reports yung...
Yeah. Right. Okay. Tapos another is, okay, there's a question here. Ma'am, saan po sa send yung pictures? Is this what you mean by yung tag dito? Yung database natin? Is
Yes
that what you
po,
mean,
ma'am.
Christian? Abay, gawa kayo! Group effort it is. So, sino yung dyan? Gagawa ng drive dyan. Tapos, sige guys, dito nyo i-post or dito nyo i-upload. Pwede ba yun? Mag-usap kayo sa inyo-inyo, then somebody make a Google Drive. Okay? Kaya ba? Christian?
Okay po, ma'am. Get pa.
Sige. So share na lang. So, dun sa Google Drive na yun, nandun na yung mga phases nyo, tapos crop na and all. Tapos, yun na yan. Download yun na lang. Okay? Okay lang ba? Atin-atin lang naman, siguro hindi naman siguro magiging, huwag nyo lang i-spread sa iba. Kung gusto nyo
Question
data
po,
privacy.
ma'am.
Yeah.
Yung pictures po, kailangan po same scene or pwede pong manghalungkat sa mga dati? Like mga old pictures namin, then or kailangan po talaga pare-parehong scene yung 5?
Hindi naman. Actually, in one case nga, iba-iba yung expression na ginawa nila eh. In some cases. Sinabi ko lang dyan, wala yung glasses. Pero actually, pwede naman. Pero, pag tumanda ka na kasi, nag-iiba minsan yung mukha mo. But, well, yeah, pwede siguro. So, looking right now at our Zoom, di ba, kayo. I can see na graduate photo yan, Ganyan lang. Siguro, ang only request ko lang is front-facing.
Okay po.
Neutral expression. Okay.
Okay po.
Front-facing, neutral expression. Okay? Sige, tanong pa.
Deeper yung orientation. Kasi di ba pag PCA compression na ganito, hindi siya rotation and what do you call this? Rotation and translation.
Hindi siya invariant sa...
Hindi siya invariant.
Yeah, which is why...
Kailangan no-centered siya.
Kaya nga 'di ba, sabi ko doon try as best as you can to align the eyes, nose, ganyan. Okay? Alright? So the more aligned the faces are, the higher the chance that you will get zero eigenvalues. Okay? Kasi highly correlated yung locations ng mga mga features natin sa mukha. Yeah.
Okay po.
So syempre madi-deform because we're going to stretch the image. So, crinap mo kanya, narrow ang face mo, tapos rectangular yung pagka-crop mo ng image, no? Tapos, i-stretch mo yan sa 50 by 50. E di, parang yung narrow face mo, naging squarish. Okay lang yun. Okay lang yun. Ano problema yan. Remember, we're just aligning things that are looking very similar. So, another thing that looks very similar, actually, is yung database of all the reflectance signals of paint pigments. Okay, so in the next activity after this, also on PCA, we will see, okay, this bunch of pigments can actually be represented in a fewer number of eigenspectra. So again PCA is useful kapag medyo parang magkakapare-pareho, may pagkapare-pareho yung data mo. Okay, it's more compressive than Fourier transform or Fourier series kapag highly similar yung mga images or signals mo. Okay? Sige, tanong pa. Any questions? None? Wala na? Going once? Going twice? Wala na? Then, let's call it a night. So, thank you very much, everybody. Group effort to ha, kaya somebody step up the plate and open a drive and then share it to the rest of the class. At dun mag-upload. Okay?
Okay. So, we use yung messenger group for communicating with the class, right?
Pwede.
Sige po.
Yes. Oo. Okay, guys? Wala na? Okay na? Going once? Going twice? Okay, goodbye. Sige, so see you again next meeting or during the tutorials. Bye, guys.
Thank you, ma'am.
Okay po.
Thank you,
Bye,
ma'am.
ma'am.
Salamat po.
Ingat lahat.
Thank you, ma'am.
Ma-
Enjoy.